The Sun. It is a star, a massive glowing sphere of hot plasma at the center of our solar system, a giant ball of burning gas, primarily composed of hydrogen and helium. Its core is a nuclear furnace where hydrogen atoms fuse to form helium, releasing an immense amount of energy. We on Earth feel its heat and see its light. The Sun's energy sustains life, drives our weather, and powers our climate systems. But the Sun also emits something else, the solar wind. This wind is invisible to the naked eye, a stream of charged particles constantly flowing out from the Sun. But it carries enormous energy and travels at incredible speeds, sometimes reaching up to 900 kilometers per second. The solar wind is powerful enough to affect our planet. It interacts with Earth's magnetic field, creating beautiful auroras but also posing significant risks. It can disrupt our technology such as satellite communications and GPS systems, and even cause power grid failures, leading to widespread blackouts. Understanding the solar wind is crucial. Scientists around the world are dedicated to studying this phenomenon to predict its behavior and mitigate its effects. We need to know how it works. By understanding the mechanisms behind solar wind, we can develop better forecasting models. We need to know how to protect ourselves from its potential dangers. This includes designing more resilient technology and infrastructure. This is a matter of space weather. Just as meteorologists study Earth's weather, space weather scientists study the conditions in space that affect our planet. Just like weather on Earth, space weather can be unpredictable. Solar activity can change rapidly, making it challenging to forecast. And just like a hurricane or a tornado, a powerful solar storm can wreak havoc. These storms can cause severe disruptions, highlighting the importance of our ongoing research and preparedness. The solar wind is a stream of charged particles. These particles are mostly protons and electrons. They escape from the Sun's atmosphere, called the corona. The corona is incredibly hot. The temperature is millions of degrees. This extreme heat gives the particles in the solar wind their incredible speed. The solar wind travels at speeds of hundreds of kilometers per second. It takes about 2 to 4 days for the solar wind to reach Earth. The solar wind is constantly flowing. Sometimes it's a gentle breeze, other times it's a raging storm. Fortunately, Earth has a natural defense against the solar wind, the magnetosphere. The magnetosphere is a region of space surrounding Earth. It is controlled by Earth's magnetic field. This magnetic field acts like a shield. It deflects most of the charged particles in the solar wind. The magnetosphere is essential for life on Earth. Without it, the solar wind would strip away our atmosphere. The surface of Earth would be exposed to harmful radiation from the Sun. The magnetosphere is a powerful force, but it's not invincible. Sometimes the Sun releases sudden bursts of energy and particles. These are called solar flares and coronal mass ejections, or CMEs. Solar flares are like giant explosions on the Sun's surface. CMEs are massive eruptions of plasma and magnetic field. Both can release enormous amounts of energy. When a solar flare or CME is directed towards Earth, it can cause a geomagnetic storm. This is a disturbance in Earth's magnetosphere. Geomagnetic storms can last for hours or even days. During a geomagnetic storm, the solar wind can penetrate deeper into Earth's atmosphere. Section 5. Power grids at risk. The 1859 Carrington Event. One of the biggest threats from solar storms is to our power grids. These grids are the backbone of our modern society, ensuring that electricity flows seamlessly from power plants to our homes, businesses, and essential services. Power grids are networks of transmission lines that carry electricity from power plants to homes and businesses. They are complex systems that require constant monitoring and maintenance to function correctly. During a geomagnetic storm, the solar wind can induce currents in these transmission lines. These storms are caused by solar flares and coronal mass ejections from the Sun, which send charged particles hurtling towards Earth. These currents can overload the grid, causing blackouts. The induced currents can be so powerful that they can damage transformers and other critical components of the power grid, leading to widespread power outages. In 1859, a powerful geomagnetic storm, known as the Carrington Event, caused widespread telegraph outages. This event is named after British astronomer Richard Carrington, who observed the solar flare that triggered the storm. Telegraph operators reported sparks flying from their equipment. The storm was so intense that telegraph systems, which were the cutting-edge technology of the time, were overwhelmed by the induced currents. Some even received electric shocks. The telegraph lines themselves acted as giant antennas, picking up the geomagnetic energy and causing dangerous surges. If a similar event were to happen today, the impact on our technology-dependent society would be catastrophic. Modern power grids are far more extensive and interconnected than the telegraph systems of the 19th century, making them even more vulnerable to such geomagnetic disturbances. The cascading effects could disrupt not only power but also communications, transportation, and even financial systems, plunging entire regions into chaos. Section 6. Satellites and GPS. Vulnerable to solar outbursts. Satellites are another piece of critical infrastructure that are vulnerable to solar storms. Satellites orbit Earth high above the atmosphere. This makes them exposed to the full force of the solar wind. Geomagnetic storms can damage satellite electronics. They can also disrupt satellite communications. GPS, or Global Positioning System, is a network of satellites that provides location and time information. GPS is used in everything from navigation systems to financial transactions. Solar storms can interfere with GPS signals, causing inaccuracies and outages. Section 7. Astronauts in danger. Spacewalks and radiation. Astronauts in space are also at risk from solar storms. Outside the protective shield of Earth's magnetosphere, astronauts are exposed to the full brunt of solar radiation. During a solar storm, radiation levels can increase dramatically. Exposure to high levels of radiation can lead to radiation sickness. It can also increase the risk of cancer. Solar storms can also pose a threat to spacecraft. They can damage electronics and disrupt communications. Section 8. Communication breakdown, solar storms, and radio waves. Solar storms can disrupt radio communications. This is because the charged particles from the sun can interfere with the ionosphere. The ionosphere is a layer of Earth's atmosphere that reflects radio waves. Disruptions to the ionosphere can cause radio blackouts. These blackouts can affect a wide range of radio communications, including high-frequency radio, which is used by aircraft for long-distance communication, AM radio broadcasts, and GPS signals. Section 9. Predicting the Sun's Fury. Space Weather Forecasting. In this section we delve into the fascinating world of space weather and the efforts made to predict and mitigate its effects. Scientists are constantly monitoring the sun for signs of solar activity. They keep a vigilant eye on the sun's surface, looking for any unusual behavior that might indicate an impending solar event. They use a variety of instruments, both on the ground and in space, to track solar flares, coronal mass ejections, and other space weather events. These instruments include advanced telescopes, satellites equipped with specialized sensors, and ground-based observatories that provide real-time data. This information is used to make space weather forecasts. By analyzing the data collected, scientists can create models that predict the behavior of solar storms and other space weather phenomena. Space weather forecasts are similar to weather forecasts on Earth. They provide detailed predictions about the likelihood of solar storms, their intensity, and their potential impact on our planet. They provide information about the likelihood of solar storms and their potential impacts. These forecasts are crucial for preparing for and mitigating the effects of space weather events. This information is used by governments, businesses, and individuals to make informed decisions about space weather risks. Governments can take measures to protect critical infrastructure, businesses can safeguard their operations, and individuals can stay informed about potential disruptions to communication and navigation systems. Section 10. Preparing for the inevitable. Protecting our technological world. While we can't stop solar storms, we can take steps to minimize their impact. This includes hardening our power grids to make them more resilient to geomagnetic disturbances, designing satellites and spacecraft with better radiation shielding, and developing backup communication systems that are not reliant on the ionosphere. Preparing for solar storms is an investment in our future. By understanding the risks and taking steps to mitigate them, we can protect our technology, our economy, and our way of life. Section 11. Conclusion. Respecting the sun's power. The sun is a powerful force of nature. It gives us life, but it can also pose a threat to our technological civilization. By understanding the dangers of solar storms and taking steps to prepare, we can live in harmony with our nearest star. We must respect the sun's power. We must also appreciate its beauty. The sun is a constant reminder of the vastness and wonder of the universe.